This is again a compression technique called as transform coding. Now if we are having a quantizer over here, obviously the reverse operation for quantizer is not possible. We have seen it earlier also कि quantizer का operation reversible नहीं होता है, तो जो भी image decompression के बाद मिलता है that is a lossy image. Lossy image means some kind of information is lost in the process of compression and decompression. So now what we do basically in this approach is we divide the image into n by n sub images. So your input image is capital M cross capital N. So that is the dimension of your input image. You take that image and you divide that image into small images, and then on each image you perform this entire process. So the very first process is forward transform. What is this forward transform can be? It is a reversible linear transformation. Okay, so it can either be Fourier transform or it can be a DFT, that is discrete Fourier transform. That again depends on you what kind of transform you want for your application. Then comes the quantizer, where the set of coefficients that we have got from the forward transform, they are quantized. Now when they are quantized, we are losing out on some information. Now quantization में होता क्या है, coefficients जो हमें मिलते हैं forward transform से, उसमें से ऐसे जो coefficients होते हैं which are small in dimension, they can be quantified grossly, or even if they are very small, very negligible, then they can be completely discarded also. And the distortion that they result in the final image, that is negligible. So only small distortion is there in the image, so that is okay. Okay, major changes not there. And then comes symbol encoder. We all know कि variable length and fixed length coding, we have seen how the coding are done. Okay, and then what you get is a compressed image. Now the next thing is, once this compressed image is there with you, what you do is you first use the symbol decoder on it. As I always tell you कि decoding में sequence becomes reverse. The sequence becomes reverse. So what is going to happen now? पहले symbol encoder था, अभी symbol decoder होने वाला है. Then inverse transform. Obviously there is no reverse operation for quantizer, so inverse transform will take place, and we had constructed a n by n sub image. Now we'll have to merge that sub image so that we get back our original image. So this is how it is done. Okay, now the sub images are usually you can randomly decide the size of your sub image, or you can go by the formula n by n raised to 2. Okay, so in that range you can have the number of your sub images. Okay, now why we are having this sub images? What is the reason for having the sub images? What happens is we are performing some transform on it. Now whatever these coefficients are there, which we get as output of our transform, they have least effect on the consistency of sub image. So many a times जो पिक्सल में correlation होता है वो हमें break करना है. Only then we will get small coefficients. If there is correlation between the pixels, जैसे पूरे image के pixels में correlation होता है, correct? So we don't want that correlation, because if that correlation is there, the coefficients will be of higher length, and we want to limit that. Okay, so to decorrelate the pixels of any sub image, that is the reason of dividing the sub image. Okay, now the next thing that we have is predictive coding. Now predictive coding comes in two types. The first one is lossless predictive, second one is lossy predictive. Okay, the first one is lossless predictive, second one is lossy predictive. Now lossless means you are not going to lose out anything, so your the original image and the decompressed image will be exactly same. No information is going to be deleted from the image in the process of compression and decompression. Okay, now how does it look like? Have a look at this. This is the encoder and the decoder for the predictive lossless predictive coding. Okay, so basically what we have is we are trying to predict En. Now how is En predicted? Fn minus f cap n. Okay, Fn goes to the predictor. Whatever is the answer of the predictor, we convert that into, we round it off to the nearest integer. That's the reason there's a box called as nearest integer over here. Okay, and what is the answer of that? F cap n. Now the difference between this is nothing but your En. That goes to the symbol encoder. Symbol encoder will give you the compressed sequence. Now that compressed sequence goes to the symbol decoder. You get En back. And now you perform the reverse operation to get Fn. So obviously, how will I get Fn? En plus f cap n is what is going to give you Fn. Okay. So this is the formula that I told you. Ki En plus f cap n is what is going to give you Fn. Okay. Now, how does the predictor work? Fn is a predicted value, correct? So how does this predictor work? How does this predictor calculate f cap n? Okay, first of all I told you कि predictor का answer जो भी है you have to round it off. Okay, then how does the predictor work? Summation of I is equal to 1 to m. Summation is nothing but simple addition. Alpha I f of n minus I. So m is a linear predictor order. Round is a function as we all know. Okay, and alpha I we consider for I is equal to 1, 2, 3, 4 up till m coefficients of prediction. So alpha I are nothing but they are coefficients of your prediction. Okay, now in case we are having x as well as y, then how the equation will look like? In 2D the predictor will become, for I is equal to 1 till m, alpha I f of x comma y minus I. Okay, now in lossy predictive coding, what happens? In lossy predictive coding, as I have told you earlier also, whenever there is a quantizer, you lose out on something. Okay, so there are certain things which you cannot recover. So if you see the compression part and the decompression part, you will notice that the decompression part is very, it is same as your lossless predictive decoder. Only change is there in the compression part. What element has been added in the compression part? The quantizer is added. So whatever En values are generated, they are quantized. And then they are going to the symbol encoder. Okay. The predictor process is the same. The predictor process is the same. The formulas are also the same. Okay. Now, let us understand this concept. You have something which is called as optimal predictors. So, optimal predictors are used by most predictive coding application, which limits the mean square prediction error of the encoder. Okay, and how is it denoted? It is denoted like this. Okay, I am not reading out the equation. You can just read out the equation. You can see on the screen. Okay, the equation goes like this. E stands for your optimal predictor. Rest all symbols you already know. Correct? This is subject to the constraint that f dot n is equal to e dot n plus f cap n, which is similar to En plus f cap n. Why are we saying that E dot n is similar to En? I showed you in the diagram over here. E dot n is just the quantizer output. Okay. The optimization criteria is chosen in order to minimize the mean square prediction error. So we want to assume that the quantizer error is minimal. So basically यहाँ पे concept यही है कि हमें ऐसा quantization process ढूंढना है जहाँ पर this particular error is minimized and E dot n is almost equal to En. Okay. Now the predictor is restricted to the linear combination of M of the previous pixel. These constraints are not necessary, but at the same time, they greatly simplify the analysis and reduce the computational complexity of the predictor. Why are we doing all these things? However your predictor is working, it should not be very complicated. Okay? And once we are doing this, once we are having this criteria in place, optimal predictors we are using, then this technique is called as differential pulse code modulation, DPCM. Now the next concept is wavelet coding. Now we have not seen the concept of wavelet, so I don't expect you to understand this completely as of now, but just understand that whatever is the concept of wavelets, we can use those wavelets to reduce the size of our images. Okay, and what we are trying to do is, we are trying to find out coefficients of the transform that will decorrelate an image's pixels that can be coded better than the originals. Because if there is correlation, then it is going to take more memory or more length of coding. Okay, so we have these small number of coefficients as a basis of transformation, and the remainder of coefficients can either be quantized or truncated to 0. Okay, and that will not result in a distortion in the image as we had seen earlier also. Okay, now how does wavelet transformation take place? Simple. Whatever we had seen in transform coding, similar thing is happening over here, but instead of the transform coding, we are having here wavelet transform and inverse wavelet transform. Now again, wavelet transform is reversible, symbol encoder is reversible, but quantizer is not reversible. And जैसे मैंने पहले भी बोला था कि एनकोडिंग के वक्त जो ऑर्डर होता है वो ऑर्डर रिवर्स हो जाता है डिकोडिंग के वक्त. ओके, now the coefficients that have little visual details or intercoefficient and coding redundancies can be reduced and the things can be quantified. Okay, अभी अगर ट्रांसफॉर्म कोडिंग में भी सेम चीज होती है तो फिर वेवलेट ट्रांसफॉर्म क्यों है? Why we have wavelet coding? The reason is very simple, because in transform coding we had to divide our image into sub-images. Okay, here we do not need to divide our image into an sub-image. जो भी ओरिजिनल इमेज है डायरेक्टली उस पे वेवलेट ट्रांसफॉर्म अप्लाई करो, क्वांटाइजर अप्लाई करो, एनकोडर अप्लाई करो, and then while decoding do the reverse job. Okay, as simple as that. Now the next thing that you should understand is there are different wavelet options which are available for you, and you can decide which one you want to choose. Okay, so if you see the table over here, you can see that there are 4 different types of wavelets which are discussed. Okay, so filter tab, scaling plus wavelet, and zeroed coefficients. The numbers are given over here and here the percentage is given. Now the question arises, what is the meaning of all these things? Now let us try and understand the meaning of all these things. So basically when I talk of filter tabs, what does it mean? So filter tabs refers to the coefficient of filters used in the wavelet transform. So I think the meaning of filter tab is very clear. So these filter tabs, they are fundamental to the process of decomposing and reconstructing the signals by using the wavelet. So there are 2 main types of filters. One is a scaling filter, which is also known as low pass filter, and another one are wavelet filters, which are known as high pass filters. So now you understand the concept of these values. Ki this value tells you how many scaling filters are used, and this value tells you how many wavelet filters are used. Low and high value filters respectively. Okay. Now, What is zeroed coefficient? It refers to a setting certain filter coefficients or wavelet transform coefficients to 0. So I'm going to set certain coefficients to 0. Now this technique is often applied for various purposes such as signal compression या noise reduction या sparsity promotion. So basically we are applying this concept for what? Reduction. So जितना ज़्यादा percentage of zeroed coefficients होगा उतना ज़्यादा reduction होगा. Okay, so it is as simple as that.